We're going to start in on Boolean algebra today. There are. This is going to get a little technical in what an algebra is, which is useful to know. Two-valued Boolean algebra is what we're going to deal with in this class. It is an algebra defined on a set with two elements. Zero and one. Okay? And there are two binary operators and a unary operator. And let's do a star, which is A, B, out. And or, this is a plus. It is these are binary operators. They take two inputs. They take in two values and output one value. The unary operator is the not, which is the apostrophe, and it's A, 0, 1, out, 1, 0. We've covered this before with the basic gates that we covered in the last week or two. But these are the elements that go into the two-valued binary that are Boolean algebra. Okay, now the rules are the axioms that and postulates that make up the two-valued Boolean algebra. The first one is that the structure is closed with respect to the two binary operators and one unary operator. That means that regardless of the input, if the input is a member of this set, the output is a member of that set as well. So, closed. So, you don't have an input into these operators that has an output that is not in that set. And you can see that from the tables that we already know. So it is closed on those operations. The second axiom or postulate or whatever the technical term is, the element, let's see here, identity elements So if you have 0 plus 0, it's 0. 0 plus 1 is 1, and 1 plus 0 is 1. Therefore, the identity element for the for plus is 0. If you OR a 0 with another element, another value, it returns the other value. It's the identity. The identity element for AND is 1. If you AND a value with 1, you get the original value. 1, 0, 0, 1 yields 0, and 1 ANDed with 1 is 1. So it is the identity element for the AND operation. The commutative law applies. Number 3. You can see that 0, 1 has the same output as 1, 0 in both the and or. So it is the commutative law applies. It is distributed. You can use the distributive law. Now this is a little bit different from regular algebra that you learned in math class. And since we already know the tables, we can go ahead and erase these for right now. Could have done them a little bit smaller so I'd have more room. But if you have A and times and B plus C, it is equivalent to it is equal to A plus B and C, A plus C. Now that's the same as in regular algebra, right? The distributive law. Where it gets a little bit different is that it is that makes it what is the term here? It is distributive. Let's see here. The operator AND is distributive over OR, which is this form. It also works the other way. A plus B and C is equal to A and B plus A and C. This is not the same as regular algebra, but it does work in Boolean algebra. It can be verified through truth tables, so you can see the equivalence. Actually, let's go ahead and do the second one to show that it is A, C, B, and C, A, and B, A, and C. A, and B, plus A, and C. All right, so go a little small here. All right, and B and C is going to be 1 here and 1 here, and 0 everywhere else. And A and B are going to be 1 down here and 1 down here and 0 everywhere else. And A and C are going to be 1 here, 1 here, 0 everywhere else. Yeah. And so A or B and C. So let's see here. B and C is 1 here and 1 here, and A is 1 for those 3, and 0, 0, 0 there, and then A and B. Wait a minute. B and C. A and C. Oh, A and C. Oh, I missed one here. Missed one here. A and C is right here. And no, yeah. Something's messed up here. A and C is there. A and B is there. B and C. Oh. Huh? Did I miss something up here? Oh, I wrote this wrong. Times Oh, that's right. A plus B, and this is A times B plus A times C. I got them backwards. That's where I was screwing up. So this is it's supposed to be A plus B. And this is alright. So sorry about that. So A plus B is going to be 1, 1, 1, and 1, and 1. And A plus C is going to be 1, 1, 1, 1, and 1. Alright, got it. Now, so the and of these two columns here will yield 0, 0, 0, 1, 1, 1, 1, 1, which is equivalent to these two here. My apologies for the mix up on the two. It's a little confusing to the distributive law as far as the Boolean algebra is concerned. But yeah, it does work out with the A plus B and C equaling to A plus B and A plus C. All right, now the fifth postulate is from the component, or complement, sorry. It is, let's see here. There is a inverse. What is this called again? Okay, for every element X in B, there exists an element not X that's also an element of B that is called the complement, such that so that X and not X equals 0, and X or not X equals 1. That is the complement. There is a complement for each element of the set. The set only has two numbers, 0 and 1. The complements are 1 and 0, respectively. 1 and 0, or 0 and 1, is going to be equal to 0. 1 or 0 is going to be 1. 0 or 1 is going to be 1 as well. So that's the complements. Finally, kind of a gimme, is the postulate that says that there has to be at least two values in the set of values in the algebra. So we saw before I erased it, B has two elements, so and they're not the same, so that postulate is satisfied as well. So from this we get some other interesting laws. I don't remember. Let's see here. They have names, and where are the names? They're not giving names. But some easy ways to ways to manipulate things and simplify equations. We have the distributive law, which we covered, the commutative law, which we covered. We also have I want to say it's the identity law, but don't quote me on that. Where you have x or 0 equals x. So if you run across x or 0, it's going to be x. Also goes with that is x and 1 equals x. So if you see an and 1, you can just eliminate the 1 and leave the x behind. X, the complement, we already covered. So let's see here. The complementary. Oh yeah. If you see x or x, it equals x. X and x equals x. So that can be easily simplified. Double negative. X prime equals x. So here we did the commutative, distributive, associative. Okay, yeah. X plus y plus z equals x plus y plus z. And likewise, x and y and z equals x and y and z. No, this is the associative law. Yeah, the associative law. No, this is the identity, and this is a simplification. This is double negative. This is the associative law. I'll have to get back to you. I thought the book had the names of those first few. Double negative is right though, but Oh, here's one. The absorption law. Let's see here. The absorption law is, let's see here. X or XY, X and Y, equals X. Right? Yeah. Because no matter what Y is, if X is 1, X will be 0. If X is 1, the result is going to be 1. If it's 0, this will be 0, and this will be 0, making it 0. So it absorbs the Y in the equation. Same can be done with X and X plus Y. That also equals X. This is absorption. Absorption. I don't know how to spell. And this is associative. This is double negative. And those, I'm not sure what those the names are on those. Now, one law is named after a person, De Morgan's law. And X and Y. This is De Morgan's laws. Okay. Yeah. Now, all this is, you learn all this so you can manipulate various expressions to reduce the amount of gates used. For example, De Morgan's law. This on the left, in both cases, use 2 gates, an and a not. Whereas over here, you use 2 nots and an or. So you can reduce the gate count by 33% by utilizing De Morgan's law. Absorption, 2 gates, and 2 gates reduced down to just 1 line. No gates at all. Double negative, 2 gates to no gates. Likewise, 1 gate to no gate. And manipulate them in most cases like normal algebraic equations with however many variables that you have. Let's see here. Does it have any good examples? I'm going to come up with some examples to go with for next time, but I think we can leave it at this for right now. Where are you guys at in the lab? What have you guys done? Gates, resistors, and LEDs? Not combining gates together, just the basic gates?
You combine it in NAND gate.
Okay, okay. Well, I don't remember the exact progression of labs, but Monday I'll give you some more examples of Boolean algebraic manipulation of expressions, and we'll go from there. But yeah, that should be it for today. Have a good day. Have a good weekend. See you on Monday.